Hello everyone. In this part I'm going to introduce the power flow analysis. What do we mean by power flow analysis? Its power flow studies consists of calculating the voltages, that's magnitude and angle, at each node or bus bar of the network, and the real and reactive power. Of course, if we know the voltages, we can calculate the real power P and reactive power Q. Why do we need to do that? Engineers will need to do that to investigate the effect of changing the circuit, if addition of loads, or expanding the circuit, adding a new link, and to see how can they modify an existing network in a most economical way to cater for increased demand or additional loads. Also, this would help to investigate the effect of loss of generation or loss of transmission links, if you're taking a transmission link out for maintenance or if there is a fault. So basically, it will help the power engineer to decide on the security of the system under various scenarios. And more now, we use power flow analysis to determine optimum system operating conditions. Optimum, I put it in italic here. It means the most economical way of operating the system.
As practicing engineers, you would not be solving power flow or load flow problems by hand. What you will be doing, you will perform full studies using sophisticated software, and you will be investigating the effect of changing the network on the power flow problem. For example, for the network shown here, the pie charts show what percentage of the line is utilized, and if you wanted to take the line between bus number 2 and bus number 3 for service, out for service, you open the circuit breaker, you see that you will increase the loading on the line between bus number 1 and bus number 2 to 93%. That's too dangerous. But what you can do is, during that maintenance period, now just a note, this is 93% load. What you can do is, you go to this load and you add compensation, static VAR compensation. Now the load is 200 megawatt, 100 megavar. If I can edit it, load information dialog, I will just edit it quickly. I will make it 20 megavar, which I added 80 megavar compensation. I will open this line now. You see it's still safe to take the line between bus number 2 and bus number 3 out. This is the sort of work you will be doing. You will be comparing the megawatt at the sending end and the megawatt at the receiving end and calculating the losses and improving the line. You would not be solving by hand any problems. I will cover the theory very quickly because you need to appreciate how the power flow problems are solved. But in my views, you don't really need to practice anything by hand. What you need to practice is how to modify network, how you get results, and how you understand these results.
Now we go to some theory, and what I'm going to do here, I'm considering a 4-bus network, bus 1, 2, 3, 4, 2 generators and the load, and should be a load here, something, it doesn't matter now. And to start the analysis, I'm just going to look at one bus and the bus number 2, and I'm going to calculate the current out of that bus. The current out of bus 2, I changed the impedance with admittance, so going to bus 1 will be V2 minus V1 multiplied by Y12, and on the other side, from V2 to V4, it will be the difference between V2 and V4 divided by the impedance or multiplied by the admittance. That will give me the current going in this link and in this link. However, if these transmission links were long transmission lines or medium transmission lines represented by their pi network, what we do is we normally ignore the losses to the ground. We just add the capacitive element, and there will be some current going at the sending end to ground and some current going at the receiving end to ground. What we normally do, we divide the total capacitance in two halves, and half at the sending end, half at the receiving end. With that in mind, the total current leaving bus number 2, which has voltage V2, there will be an element here, a capacitance connected to ground like this one, and there will be some red current, and also on the other link there will be capacitive current. These currents are shown here in red, and Y120 is the transmission line between 1 and 2, 0 is to ground, multiplied by V2 will give the current going at this end. Y240, 24 is this link, so it is actually this element of this transmission line. Now we have an equation giving us the current I2 out, total current out of bus 2. I will rearrange it, I collect terms, and I will end up with minus Y12 V1, it comes from this element, and so on. You can check it. The main thing here, you look at the element multiplied by V2 is Y12 plus Y24, that's the admittance of this link, admittance of that link, plus Y120, Y240, the pi connection, the B of the network at both ends. And then it's minus V4 multiplied by Y24, minus this. Okay, so bearing that in mind, we look at this network now. We try to write down the current out of each bus in terms of the admittance of the transmission links and also to ground. So I1, bus bar 1, is connected to 2 and to 3. So, well, I just mentioned before that this is the sum of the admittance connected to the bus bar. We'll do that for I1. The sum of the admittance connected to bus bar 1 will be Y12 plus Y13, that's correct, plus the charging elements here, Y120, Y130, multiplied by V1. Then it will be between 1 and 2, Y12, negative 52, and in V3 it will be this admittance and negative. Similarly, you can write down for I3 and I4. So now we have the currents out of the buses, each bus. Y11, Y122, the diagonal element, I'm going to put this in a matrix, for any bus bar are the sum of all the elements, including to ground, connected to that bus. And the off-diagonal elements are the negative value of the admittance of the transmission link between the lines. Between 1 and 3, there is minus this. Between 3 and 4, there is minus this. There is 0 between the others. So we put this in a matrix form, end up with this diagonal element. The off-diagonal elements, for example, I look at Y12 and Y21, are these. It's actually this element. So these are equal and equal negative value of this admittance. Similarly, Y13 and Y31. I have to point out here, lowercase y is the per unit value of the transmission line admittance. The capital is the element of this matrix, which we are going to call it the bus admittance matrix. The off-diagonal elements are all also equal. Y14 equals Y41, and bus number 1 and 4 are not connected, so it's 0. And you will check the equations, you will find that I1 and I4, I1 doesn't have V4 and I4 doesn't have V1, and so on. So this is the bus currents. I bus equals Y bus multiplied by V bus. We can put this as a sum. Current I1 is sigma. We have how many buses? We have 4, so from J equals 1 to 4, that's the number of buses, of the elements of the admittance matrix in the first row multiplied by the voltages, with J changes from 1 to 4. For any general bus K, IK will be YJK, VJ, and change J from 1 to N. We'll take this equation to the next page and N a number of buses in the system. However, we also know that the complex power is V multiplied by I conjugate. So if I'm looking at bus K, this is the current out of the bus. If I multiply the current, I get the conjugate value, and multiply by VK, I get SK here. This is the complex power flow at that chosen bus K. At this stage, we have to make observation. This is the basic power flow equation that we need to solve. First thing is, it's nonlinear. Nonlinear because it has the voltages multiplied by each other here. And there are 4 unknowns. For each bus, we have 4 unknowns. The total power, if we have, this is the power, complex power flowing out of the bus. If we know the total power flowing into the bus, we can make this S flowing in equals to S flowing out and solve the equation. In general, we have 4 unknowns and we need to know 2 of them. So the problem consists of solving nonlinear equation constrained by terminal relationship. Terminal relationship, it means if it's the bus has a load and the generator, then the load will be negative power because it's coming out of the bus. The generator, it will be negative plus P and plus Q. You add and subtract and you end up with the net power into the bus. However, while in theory, if we know the bus voltages, we can calculate the power flow in the branches. In practice, that doesn't work because we cannot calculate the power flow unless we know the power losses. The power losses in the branches are unknown. And because they are unknown, that complicates calculations and makes it impossible to calculate unless we assume that somewhere in the network there is a very generous large bus that will provide all the power loss in the line and all the reactive power is stored on the line. And that we call the slack or a swing bus. In any load flow problem, one bus has to be assigned as the slack bus or swing bus. For that particular bus, we'll assume that the voltage and the angle are known. Normally it's 1 per unit and 0 degrees, and the unknown are the P and Q. And this P and Q of that particular bus will furnish, among other things, all the power lost in the system, as well as all the reactive power stored in the system. That's why we need a slack bus. It doesn't matter what method you use to solve. A slack bus will have to be identified. Now back to this equation, and we're going to solve it for one case using the Gauss-Seidel iterative method. Why iterative method? Because the equation is nonlinear. We look at the bus K. And for bus K, suppose we have an estimate for all the voltages of the network. And we can partition this equation into this form, just taking bus K calculation out and putting it there, separating it from this term that does not include Vk, the voltage of bus K. And for a load bus, we would know the reactive and active power. They are, if it is pure load, it will be out of the bus. So to make them into the bus, we'll use negative values of the load. And in this case, we substitute the input P and plus JQ equal to the output of the bus. Rearrange the equation, end up with this equation in Vk. So what do? From the start, we assume we know estimates of all the voltages, normally 1 per unit and 0 degrees. Use this assumption to calculate, including for Vk and the given P and Q. We use them to improve the estimate, calculate the voltage, a new value which is improved, converging to the real value of Vk. We do it once, so we have an improved value for Vk. We do it for the other voltages, we have improved value for the other voltages. Then we can repeat the process again and again and again until we find that the difference between two consecutive calculations of the voltages are within tolerance. Tolerance is 10 to the minus 10 or 10 to the minus 11. Very tight tolerance. So this is summarized in the next slide. This is the equation we used for the load bus. There are two situations here. A simple method known as just the Gauss method. It waits for all the voltages to be calculated and then apply the new values in the second iteration or the following iteration at the same time. Gauss-Seidel is an improvement of the Gauss method, in which as soon as we have an improved value for a bus voltage, we immediately use it in the computation of all other voltages. And the Gauss-Seidel converges quicker than the Gauss method. I have to point out that this equation we arrived at assuming P and Q are known for a load bus. These are the constraints of the bus. This formulation only works for the load bus. There are other equations for other buses. For example, a generator bus, if it's a pure generation, then we know that the operator can adjust the excitation to maintain the voltage at constant value. So, for example, for a generator bus, you can have the known values as the magnitude of the voltage and the magnitude of the power P coming out of the generator. And then the unknown will be the angle of the voltage and the reactive power. The slack bus, we assume that both voltage, magnitude, and angle are known, and we try to find P and Q. Other methods, of course, are used, and we are not covering them here. All what I wanted to do in this very brief part is to give you an idea on what happens inside the sophisticated software. Quite frankly, this is mathematics, and if you covered it in mathematics, good and well. If you didn't, well, just know how the iterations are performed and how the specified tolerance will affect the final value you get, the accuracy of the final value you get. Gauss-Seidel method is not used in commercial grade software now because there are other methods which are computationally more efficient, Newton method namely, and these are the method. This is actually one of the methods which we will use when we come to the application using the Power World software in part 2. But we continue on this part 1 and try to see how we can apply Gauss-Seidel. This used to be the case about maybe 20-30 years ago. Engineers used to write a small software to calculate the voltages. And for example, like this, and here the impedances are given per unit. And for example, like this, I wrote a small MATLAB program. What it does, this MATLAB program, it takes the Z's and then formulates, it does calculations, and at the end here will give me many outputs. I can define what I need, but it gives me the final value of the voltages. Note here that bus number 5 has a magnitude of 1 and angle 0. That actually was our slack bus. We defined 0 angle and 1 per unit magnitude. The other buses settled at a certain value, real and imaginary, which actually magnitude and angle. So that's what a computer program that could have taken several hours, maybe days to write in the 1980s or even 90s, that's what a computer program would give you. I used the MATLAB, but there were other languages that could be used to program the technique. But this is not what we need. Today, the work of a power engineer is much more complex than just calculating voltages at buses at one point. As I said earlier in this presentation, the practicing engineer will be looking at something like this and opening circuit breaker, and he can see immediately what will happen to the loading in different lines and what will happen to the voltages. How will the voltage collapse or will it stay within limits? He will have to modify and so on. So this is what was done at least 2 decades ago, and this is what you as now a student to be an engineer will be using. And this will be covered in detail in the second part of the presentation, part 2 of the power flow analysis, which I believe is already posted on Blackboard. If you are interested in a copy of this simple MATLAB code, your local tutor will be able to contact me and get a copy of it. I actually give some tutors a copy of it. So what we're going to do in part 2, we're going to work on an industrial grade software and investigate how the practicing engineer would deal with the power flow problem. See you next time.